All right, peeps, how are you? We're back. I'm going to try to do something here where I'm going to try to get this screen over here. Yeah, that'll work out, right? Yeah, put it right there. Sweet. All right. And I'm going to have to put this somewhere too. Sorry, everybody. Trying to fix the screen here. Throw that there for the moment. I'm not going to need that. All right. All right, here we go. We left off, I believe, with talking about carbon flows. Carbon's obviously a cycle. You don't make new carbon. You don't really destroy it either. You just put it in different places, which is what gets humankind in trouble. Do me a favor, define carbon fixation. If you're listening to this, with carbon fixation is where you basically lock it up in something solid. So, like trees, carbon fixation, you're locking that carbon up and for a pretty long period of time. Unfortunately, when you cut down trees and you burn them, that's when you run into issues. You got the four stages of carbon. You've got four stages of the cycle, I should say. You've got soil, which is where you've got carbon in the soil. Then it takes it up with plants, biomass. Then it basically breaks down either naturally or we burn it, which is the problem right now with fossil fuels, and runs off into the ocean. I'm sorry, it goes off in the atmosphere, goes off then into the ocean, and then it repeats itself by being pressed down into soil. And when it's in the soil, it gets pressed down, and that's what forms fossil fuels, given like thousands of years. Carbon is locked up fixed by photosynthesis. So it's released by respiration in burning of fossil fuels in biomass. So plants will breathe out carbon dioxide, all right, with photosynthesis. That's what they do. They also produce heat and water vapor. So it's almost like a chemical reaction. Like add these two things together, equal sign, you have these three things. So you have heat, water vapor, and carbon dioxide. Oh, this one here should be in green if you're looking at this. We're going to highlight that. Knew there was something I forgot to do. Over here and highlight and green. There we go. So relate a compost pile in the winter to the carbon cycle. So if you're listening to this, this is how we're going to relate a compost pile to carbon cycle. Compost pile has bacteria that decompose the the plant material, for lack of a better word, and the carbon basically goes. You produce heat with the compost pile. Even in winter, if you turn a compost pile over, you'll see it's actually steaming on the inside. So compost pile produces heat. It does produce water vapor, which is sometimes you'll see it like coming off or like crystallize. And then also too, it produces carbon dioxide. So plants grow and put out small amounts of carbon dioxide to the atmosphere as they grow. Then they die and contribute more carbon to the atmosphere. But most carbon is locked up as sediment, eventually fossil fuels. So that's what you have with a plant cycle. You've got a plant, it absorbs carbon, it releases it off to the atmosphere while it's living. It dies. Carbon dioxide then goes off as gas off into the atmosphere. It also breaks down and into the soil where it eventually becomes fossil fuels. Um, Volcanoes are humans burning fossil fuels release carbon dioxide carbon to the atmosphere. So even if we weren't burning fossil fuels, you would still have some in the atmosphere, which you need because otherwise this planet would be very, very, very cold. Um, we get a lot of like carbon dioxide from volcano explosions, but most of the carbon dioxide that's happening right now is from human activity with us burning fossil fuels. Eventually, rain brings it back down to the ocean, or brings it down to the land, then washes it off into the ocean. And then it falls to the ocean floor. And with the ocean weight packing it down, it eventually forms that sediment rock and fossil fuels. Uh, this system works good if it's in balance. The question that's out there right now is the carbon cycle in balance? And if not, what do we do to balance it? There's a lot of different solutions. The correct answer is probably doing a little bit of all of them. Where is humanity putting too much carbon? Change that so I don't get in trouble with the spelling department. Um, so we're putting way too much carbon off into the atmosphere. What would happen if carbon was no longer released into the atmosphere? Yeah, we'd freeze. All right. Um, Humans in the carbon cycle. We burn 5.5 gigatons of carbon per year, um, just with fossil fuels. 20% natural gas, 40% coal, 40% oil. Natural gas tends to be a byproduct of oil production, other things. Um, some stays in the atmosphere, some is absorbed by the ocean and phytoplankton, but a large amount, we don't know where it ends up, which is kind of scary. So we know out of that 5.5 gigatons, um, we know some stays in the atmosphere, some is absorbed by the ocean, phytoplankton, but a large amount, we got like no idea what happens to it, no accountability. So, um, since the pre industrial revolution, we have added 200 gigatons to the atmosphere. So, think of us with horses and buggies and little small farms and no factories. Since then, we've added 200 gigatons. Nitrogen cycle. Nitrogen cycle is sort of like, but not really, the carbon cycle. The thing they have in common is that it's a cycle. You don't make nitrogen, you don't destroy it either. It's just out there. So it's in 3 stages. Let me get this on the book though. Yeah, nitrogen cycle is on page 88. Move this on over here. Um, you got 3 stages. You got like main stages. You got fixation, nitrification, denitrification. So, you know what fixation is? It's where you lock it on up. So, nitrogen is imported for proteins. Um, Important. Sorry, not imported. So, it's important for proteins because it's what forms the building block for amino acids, which then form proteins, which then allow you to build and get bigger, whether you're a plant or animal. A lot in the atmosphere, but it's useless. Can't really touch it, can't utilize it. We've got no mechanism for utilizing it, whether you're a plant or animal. Plants can only absorb nitrogen through ammonia and nitrates, or nitrites, I should say. Um, Animals eat plants, absorb nitrogen through amino acids. So we plants get their nitrogen through the soil, and we'll get into that a little bit more in a second. We get our nitrogen through eating plants. Then what happens is with the nitrogen, we end up pissing or pooping it out. So, yep. Define nitrogen fixation for me. All right. Shouldn't be too hard. It's basically where you're locking up nitrogen. Um, Bacteria in soil fix nitrogen. So we don't really, or plants don't really like fix nitrogen. So what we, the, so in the top layer of soil, you've got bacteria, and their main, like this brand of bacteria, is basically just taking the nitrogen from the soil or from the atmosphere and making it so that plants can utilize it. Um, Nitrogen fixing bacteria living in root nodules of legume plants. This is a big one. Um, Plant gives bacteria sugars from the photosynthesis. It's called a symbiotic relationship. That bacteria gets something, and then the plant gets something. So they both help each other out. Um, the plant gives bacteria sugars from photosynthesis, and the bacteria hooks the plant up with nitrates. So cyanobacteria, which are like this blue-green algae, found in the water and in the soil. These are another one that are really big. They obviously will work whether it's water or um, soil. So lightning oxidizes nitrogen into nitrates. Yeah, you just really the amount's got to be pretty small though. I mean, we just don't run into lightning storms here in New England all that often. Maybe other places do. Um, the Haber process. This is where we make our own fertilizer. So nitrogen and hydrogen are combined under pressure with iron. The product is ammonia. So, and that's what we use to make plant fertilizers. All right. Define nitrification if you can. So it's basically where the bacteria are turning ammonia into nitrates, which then form into nitrates. And then plants take that on up, the nitrates, and they utilize it to make amino acids and proteins. Define denitrification. So this is a decomposition. Also gives nitrogen to plants. So plants die, they're broken down, so nitrogen goes to the soil. Worms, insects, and other critters speed this up. Think of compost pile. So here's that question again. How does composting supply nitrogen to plants? Simple explanation, please. So the nitrogen's locked up in a plant. Um, Worms, insects, bacteria, they denitrification. So they break down the plant, and that nitrogen in the plant goes back into the soil. So plants then build nitrogen, amino acids, proteins, build nucleotides too, which are important. Humans in the nitrogen cycle. Ooh, okay. We're down here on page 89, but I think we're going to just skip on over to 90 and 91 in case we need it. All right. Humans in the nitrogen cycle. We remove plants and animals, less nitrogen in the soil. Nitrogen then ends up in the ocean from pee and poop. Did I get that word right? Yeah. All right. Let's get this over here. All right. Humans can add too much nitrogen to the soil via fertilizer or planting legumes. So it's just like the nitrogen cycle. It's when you have, I'm sorry, just like the carbon cycle. With the nitrogen cycle, when it's balanced, everything rolls. We're going good. But the problem we are having right now is humans are adding a little bit too much nitrogen to the soil. And then there's the runoff. It runs off into streams, then into the ocean. And then we have problems. So, big time right now is like off in New England, Vermont. Vermont's a big dairy industry. They think like 30 years ago they had 10 cows for every one person. That's why they have milk up there and Ben and Jerry's and Cabot cheese. Um, so the problem you have with cows is it's a pretty good cycle or system in that you grow hay and you let the cows eat, part of the field during the summer, and then during the wintertime, I'm sorry, before the winter hits, you cut the hay and you store it, and that way you have something to feed the cows during the year. You also can like rotate your fields and grow corn as well. So the main fertilizer they use up there is something that they have a lot of cow poop. All right. But they used to just spread the cow poop onto the field like whenever, and then they would just watch it. A lot of it would run off into the streams, and with the nitrates in there, they really contribute to problems. Um, Eutrophication, really. So What they do now is they tell the farmers, they're like, okay, you can only apply the cow poop and the fertilizer onto the field at a given time. So, yeah, that way it cuts down on that junk. All right. Humans in the nitrogen cycle. Remove plants, animals, less nitrogen in soil. Nitrogen then ends up in the ocean from pee and poop. All right. So that's if you remove plants and animals. So that's where you just ends up less in the soil, which is bad because then stuff doesn't grow. Humans can add too much nitrogen to soil via fertilizer or planting legumes. So if you plant, remember how we were talking about that bacteria that's symbiotic with legumes? That actually can add too much. If you plant too many of the legumes, which are like beans, you can end up with problems with too much nitrogen in the soil. Soil, if it's too watery, bacteria won't break down and release nitrogen, at least most bacteria. If it's too dry, the nitrogen just then gets washed away when it eventually does rain. So, um, this one here has got to be green. What is eutrophication and what role does excess nitrogen in water play? So, look that up, answer that for me. Energy flow diagrams. They're easy for comparison of various ecosystems. They show energy entering and leaving. Um, so you don't always get energy flow diagrams is right here. Yep. Let's go on to the next page, which is page 2. And I somehow got to get back here. There we go. All right. Page 92. Um, assimilation and productivity efficiencies. Sorry, the book wrote it the simplest. So what I would love for you to do is copy this down here. If you're looking at the book, I want you to copy down from assimilation down to gross productivity right here. So I should probably move this. Good. All right. You're probably going to have to pause the video right here and take this down. But there are two quantities that we need to know to establish these efficiencies. So it's assimilation and productivity. What proportion of the NPP from one trophic level is assimilated by the next? So how much is taken up as we start going up the food chain? How much of this assimilated material is turned into the tissues of the organism and how much is respired? So, how much is used just with like daily living and how much is just to build and make the organism bigger? For an animal raised for meat, these questions are how much of the grass that an animal eats can it assimilate, absorb into its body? This will determine how many animals the farmer can put in a field. So that way you don't overpopulate a farm. How much of what is assimilated is used for productivity, turned into meat? On a commercial farm, this will determine the profits. So, efficiency of assimilation, gross productivity times 100 divided by food eaten. Efficiency of biomass productivity, net productivity times 100, gross productivity. So, yep, that's what we got. All right, peeps, we're going to move on here. Trophic efficiencies. All right. Putting that here. Good. Trophic efficiencies. On average, every time a trophic level absorbs another, only to 10% of the productivity is kept. It's very little. especially for plants. Um, Small mammals, low efficiency because they're warm blooded. They have a high metabolism, large surface area to volume ratio. Think of that little sixth grader that's always like running around, "Ah!" And he's always hungry, warm blooded, he's putting out heat, high metabolism. Yeah, so for them, their efficiency ratio is pretty dang low. All right, zooplankton eat phytoplankton in the ocean. They have higher efficiency. Doubt they're warm blooded. Probably got a low metabolism. Um, and they're pretty small. So digestion just by nature is inefficient because we absorb what we're going to absorb and then we poop out the rest. And it's not just us, whether you're a carnivore or an herbivore. That's what we do. All right. Heat is lost in respiration. Just with daily activities, your body is always going to produce heat. Same thing for plants, by the way. Energy budget. Measurement of energy entering and leaving the animal population. Oh, no, we're not there yet. We're right here. Page 92. Measurement of energy entering and leaving animal populations. It's useful for farming and to predict yields. It's actually not as hard to determine either. It's pretty accurate. So, human activities in ecosystem. Anthropogenic, which is the process, effect, or activity from humans. Increased greenhouse gases is anthropogenic. So, this is anything that's like a process, effect, or activity directly from humans. The concept of energy subsidy. Right here. You're going to be on page 93, 94, 95 for this one. So, generally, humans simplify nature and make it less diverse. So, when we cut and slash burn down a forest, we take a lot of different variety of trees, grasses out of the equation. And what do we replace it with? Generally, one crop, whether we're growing soybeans, corn, wheat, whatever. All right. So, not a whole lot of diversity. Also, too, when we're removing insects and weeds, we're just like, nope, we want one thing, one thing. So, when you have more diversity, especially with big farming, this is what we tend to do. Big farming requires a larger energy subsidy, so more energy going into it, more effort. Energy can come, and I gave you the definition of energy subsidy there. But energy can come in the form of labor, animal labor, or just what we do nowadays. A lot of fossilized fuels go into machines and we burn them to give us that energy and labor. So farming has become more productive, but requires more energy going into it. So big farming allows our population to be large. Um, MEDCs, like developed countries, use 50 times more energy than hunter gatherer societies. And that's a big issue because they're bringing it up in the climate committees and whatnot. That a lot of these smaller countries are like, wait a minute, we're the ones that are impacted most by climate change, and we don't even really cause it like you developed countries. Um, Energy yield ratio. Farming is like input and output, it's an engine. It really is. Slash and burn farming has a 1 to 30 ratio. It's very efficient farming. Not really sustainable, but pretty efficient. All right, so this one here, we're going to be on page 96. Very efficient farming. So, but releases tons of carbon because of burning trees. All right. Also, too, it's not as diverse. Chicken and egg farming has a 10 to 1 ratio. So you got to put in a ton of effort into chickens and egg production and to get just that little bit of energy. But the food is very nutrient dense and energy for carnivores is absorbed at higher efficiency rates. So when you eat, like vegetables, you absorb, how much of that energy. So you got to eat a lot of them. With meat, you have to pretty much eat less of it because you're absorbing more of that energy. Diverse farming means the system is less likely to fail completely. So that's a case for like rotating crops and having diversity, just on a business model. Because if you have one crop as a farmer and that crop fails, there goes you have no money for the year. So, yep, that's what we got, folks. All right. And yep, hope you're doing good. Adios. Bye. Actually, let's get